Let's look at the questions for exam 3 practice test. So let's start with 1. Question 1 involves finding the domains of these functions. Our first function is f of x equals 3 over x plus 5. So when we have a rational function, there are restrictions in the domain, and that is that just our denominator, which in this case is x plus 5, cannot equal 0. So thinking about that, we would subtract the 5 over here, and we get x cannot equal negative 5. So there we would say our domain is all real numbers except for x cannot equal negative 5. And there we go. That's how we would set up that domain. On question B, we have the same idea. X squared minus 5x minus 6 cannot equal 0. But I'm going to have to factor this. So we're going to go minus 6 and plus 1. That can't be 0. So we have that x cannot equal 6 and negative 1. So when we write out our domain, we have that x can be all real numbers except for x cannot equal 6 and negative 1. Okay, so that's finding the domain of rational functions. Now I'm going to find the domain of a radical. And it's a squared, so that means there is a restriction because the inside of my square root, when I'm talking about functions, cannot be negative. So we have x minus 5, or 7x minus 5, that has to be greater than or equal to 0. So I add the 5 over, I have 7x is greater than 5, divide both sides by 7, and we get x is greater than or equal to 5/7. Now, if you want to think about this on a number line, we have the number 5/7, and it can be equal to, we just have all the values greater than 5/7 and equal to. So when we write the domain here, because we don't just have 1 or 2 restrictions, we have like an interval of restrictions. We can't write it like we write the domain for rationals. We have a whole domain or interval that can be equal to the domain, so I'm going to use interval notation. And there we go. That would be our domain. 5/7 inclusive to infinity. So that's what we do with question 1. We just find either restrictions in the denominator, or if it's a radical, we set the entire radical to greater than or equal to 0. Sorry, the inside of the entire radical. Okay, question 2 is probably one of the harder questions we're going to have to deal with because we are talking about adding and subtracting fractions. We are going to have to find common denominators. So first thing, very first step, and this is something, if you have a note card, you might want to write this down, this process. But the first thing you're going to want to do is factor the denominators. So starting with the first fraction, we have x minus 4. It's a difference of the squares, so I have 3x plus 4 and 3x minus 4. The second fraction, the factoring is a little bit more difficult. So I'm going to come over here. I'm going to take this 3x squared minus 11x minus 20. I'm going to factor this. So let's see, we've got x squared minus 11x minus 60, which gives us x minus 15, x plus 4. Divide both sides by 3, and we've got our factoring. We have x minus 5, 3x plus 4. And then this last factoring, I probably want to also double check this factoring. So I'm going to take that x squared minus 19x plus 60. We've got x minus 15, x minus 4. Divide both sides by 3, and we've got x minus 5, that's good, and 3x minus 4, also good. So I'm going to rewrite this x plus 1, and I'm going to say x minus 5, 3x minus 4. So that might be the hardest part of these problems, is factoring the denominators. If you don't have factoring down, there are lots of resources to be able to factor. Come talk to me and I can kind of send you in the right place. Okay, so the next thing that we're going to want to do is find the least common denominator. I did erase my factoring because I know that I'm going to need that space, but we have here 3x plus 4, 3x minus 4, and x minus 5. So on my first fraction, the piece that is missing is the x minus 5. So I'm going to multiply the top and the bottom by the part of the LCD that it is missing. On the second fraction, we are missing the 3x minus 4. 3x minus 4. And on the last fraction, we are missing the 3x plus 4. Now that we have the entire fraction, all of the fractions with a common denominator, we can rewrite that over 1. So I have here x minus 5 times x minus 4 minus 2x minus 1 times 3x minus 4 plus x plus 1, 3x plus 4. And all of that is going to be over my LCD, which is the x minus 5, and then 3x plus 4, 3x minus 4. Okay, once we get here, now we just need to do some foiling or distributing. You must be very careful with your signs. That is where you will go wrong if you make a mistake. So, just kind of thinking about that, we have here to distribute this x minus 5, x minus 4 first. So if I go first, outer, inner, last, I have x squared. Negative 5x and negative 4x is negative 9x. And negative 5 times negative 4 is plus 20. So that's my first group of multiplication. The next one here is this 2x minus 1, 3x minus 4. So if I go first, that's 6x squared. Outer is negative 8x, inner is negative 3x, so that's negative 11x. And then negative 1 times negative 4 is plus 4. Okay, and then the last one here, I have this plus. So I'm going to FOIL x plus 1, 3x plus 4. If I distribute this through, I have 3x squared plus 4x plus 3x plus 4. Whoops, and let's combine those together. That's what I was doing on the other ones. So the 3x plus the 4x is 7x, and then plus the 4. Now all of this would be over our LCD, but I'm going to kind of just figure out what it is first. I'm going to distribute anything that needs to be distributed, so like this minus sign. So I've got negative 6x squared plus 11x minus 4, so I'm distributing that minus sign through, plus 3x squared plus 7x plus 4. And then from here, I'm going to combine like terms and write it all, that whole numerator over the denominator. So I have x squared minus 6x squared plus 3x squared should give me negative 2x squared. Then I have negative 9x plus 11x plus 7x. So if I go negative 9 plus 11, that's 2. And then plus 7. 2 plus 7 is 9x. And then we've got 20 plus 4 minus 4. That one's nice. So there we go. All over our LCD, which is x minus 5, 3x plus 4, and 3x minus 4. So everything is simplified. That is our final version. You do not need to FOIL the denominator, and you don't need to factor the denominator unless you think anything's going to cancel. That won't happen. It makes problems way too crazy. So we've got that. We're good. Okay, the next problem is, let's look at question B. So same thing as above. To start out, we want to factor. But in this case, we want to factor the numerator and the denominator. So what we will do is let's start with the denominator or numerator here. We have 3x squared minus 9, which can factor to 3 times x plus 3, x minus 3. My denominator there is x plus 4. It doesn't factor, so we're going to keep it. Then on my second fraction here, I have x squared minus 16. So that's a pretty simple factoring. We've got x plus 4, x minus 4. And then we have 9 times x plus 2. And then we have divided by, what do we got here? X minus 3, x minus 4 over 2x squared minus 3x minus 14. So I might want to do a little bit of work here because this is a little bit harder factoring. It's not one you can just really look at and get. Or maybe you can, and that's awesome. But we have x squared minus 3x minus 28. That's x minus 7, x plus 4. And divide those by 2. So we end up with 2x minus 7, x plus 2. Okay, so from here, I am going to rewrite this as one fraction, but I also want to keep flip change. So we keep the first two because they are being multiplied, and we're going to flip the back side and change that division to multiplication. So let's flip that 2x minus 7 times x plus 2, x minus 3, x minus 4. And since we changed that to division, I'm just going to write everything else over that. So there we go. That's a little better. We have 3 times x plus 3, x minus 3. And we've got x plus 4, x minus 4. And then on this one, we have x plus 4 times 9, x plus 2. So there is all of our stuff factored out and put just as one giant fraction. Then the fun part, you get to cancel, my favorite part at least. I have a minus 3 that cancels. The plus 4s that cancel. Ooh, I have this 3 and that 9 cancel. So 3 divided by 9 is 3 left over on the bottom. What else cancels? Let's see here. The plus 2. Ooh, the plus 2s do cancel. There we go. And, ooh, one more. That's cool. Lots of stuff cancels. That always feels fun. So what we do is we just write what we have left over. In this case, on the numerator, we have x plus 3 and 2x minus 7. And in the denominator, we have a 3. And that is it. That's factored. It's factored and multiplied through and simplified. All right, let's go on to the second page. So it says perform the long division. So we need to set the division up. So I have x plus 3 as my divisor. That's going to go in the front. And then I have 5x cubed minus 6x plus 5. So I'm going to write those in decreasing powered order. I have 5x cubed, and then there's a problem. I don't have any x squareds in my equation, so because of that, I'm going to write 0x squareds minus 6x plus 5. Okay, now we're going to just start with this x. We're going to do division. How many times does x go into 5x cubed? Well, that would be 5x squared. So first step, always divide. Then we multiply. So we're going to take that 5x squared and we're going to multiply each thing. So that gives me 5x cubed and 15x squared. Both of those are positive. We're going to make sure we change each thing's sign. And that becomes 0 for my x cubed terms. And 0x squared minus 15x squared is negative 15x squared. Then I'm going to bring down this negative 6x and bring down this plus 5. Okay, now we're going to take this x and divide into the negative 15x squared. So we get here negative 15x. Okay. Then we do the multiplication, so that's negative 15x squared, and that's negative 45x. Okay, then we're going to change each thing that we're subtracting sign, because that's what subtraction is just changing the sign. Here we get 0. 45 minus 6 is 39x, and we'll bring down that 5. Then we're going to find how many times x goes into 39x, so that's 39. And then multiply, we've got 39x. And 39 times 3, let's see, that's 7. Carry the 2. 3 times 3 is 9, plus 2 is 11. So, 11, 17. We're going to go through and change each thing's sign. Subtract, subtract. That's 0, and that's negative 112. So my final answer, the answer to the division is 5x squared minus 15x plus 39. But then I have a remainder of negative 112. So I'm going to go minus 112 over whatever my divisor was. Or you can go plus negative 112. That's fine. It's the same thing. So we've got our answer. Okay, there's our division. The next question is simplifying a complex fraction. I'm only going to do A and B on this because if C is on the test, it will be a bonus question. So you can try C to practice, but I want to do one like the one on the test will be more similar to either A or B, or maybe both. 2, we have x plus 3 plus 5 over x all over 9 over x plus 3. So what we want to do is we want to find the LCD between all of our fractions. So we have, or our denominators. So there's all of our denominators. So our LCD then would be x and x plus 3. So I'm going to go through and I'm going to multiply the top and bottom by x times x plus 3. So that means I will multiply this fraction this fraction and this fraction by x times x plus 3. Okay, then from there we will cancel. So we have the x plus 3's canceling, and the x is canceling, and then the x plus 3's canceling. So in the numerator we have 2x. Then we have 5 times x plus 3 all over 9x. I will combine, or actually I need to distribute here, this 5. So that's 2x plus 5x plus 15 all over 9x. So that's 7x plus 15 divided by 9x. Okay, and my numerator does not have a common greatest common factor, so I can't simplify this. So this is the final answer. Okay, the next problem, whoa, sorry about that, is this B. The first thing that we need to do is we need to factor any of our smaller denominators. So we've got here this x over x plus 8 times x minus 8 plus 3 over x plus 8. That does not factor. And then we have x plus 2 over x minus 8. Okay, we're going to find the LCD, which is x plus 8 times x minus 8. So I'm going to multiply each of my fractions, numerators, by the x plus 8 times x minus 8. X plus 8 times x minus 8. There we go. I will cancel each of my denominators that can cancel. So we've got that and that cancel. The x plus 8's cancel. And the x minus 8's cancel. From there, let's rewrite what we have. So the x in that first fraction is all that is left over. In my second fraction, I have a 3 times an x minus 8. And in my denominator, I have x plus 2 times x minus 8, or x plus 8. I'm actually not going to factor that yet. I will distribute this 3 through. 3x minus 24. And then I have 4x minus 24. Which I can factor a 4 out, but by factoring that 4 out, I don't have any canceling. So I don't need to factor if there's no canceling. So there we go. All right, that is it for that page. Let's go on to the next page. Remember that I'm going to give you a chance to try C, but since it's a bonus question, I'm not going to do it for you. Okay, let's look at 5. We have solve the rational equation. There's actually more to this problem on the test. They do say one thing, and that is that they want you to state the restrictions. That is going to be part of solving this problem. So it says solve the rational equation, but let's also write the restrictions. Before I write any of the restrictions, we need to factor any denominators. And that just happens here. We have x minus 4, x plus 3, and that equals 8 over x plus 3. Okay, so there is our factored form. I want you to then state what restrictions there are in this problem. So if we talk about that, we have talked about that when we talked about the domain. So the restrictions is essentially nothing in the denominator can be 0. So that means that x cannot equal -3 and it cannot equal 4. So those would be our restrictions. Okay, after we find our restrictions, we need to multiply through by the LCD to get the LCD to go away. This is different than when we are adding. When we are adding, we only multiply each piece by what it's missing because we want to keep the denominator. But when we are solving, we want the denominators to go away completely. So on this first one, we're going to multiply each fraction by the LCD. So I'm going to multiply everything or every term or every fraction by that LCD. That's a +3, sorry. And we cancel out what cancels out. Okay, so here I have 1 times x minus 4 plus 1 equals 8 times x minus 4. 8 times x minus 4, yeah. Okay, so we have x minus 4 plus 1 equals 8x minus 32. Okay, then from here, oh, sorry there. I'm going to combine like terms. So we've got x minus 3 equals 8x minus 32. I'll add that 32 over to the left side and subtract the x and bring that over to the right side. So we end up with 29 equals 7x. And divide both sides by 7. We get x equals 29 over 7. And there we go. All right, let's take a look at question 6. This is the application problem. If you follow the steps, they will work you into being able to solve the problem. So just make sure you do that. So the first step is, what is the cost function of producing X clocks? Well, if we look at our problem, the fixed monthly cost, oh, there's a typo. That should say cost to run the business is $25,340. And it will cost $450.25 to make each clock. So that means that's times X for the number of clocks. So that's our cost function. Okay, the next thing they want is the average cost. So to find the average cost, here we will go 25,340 plus 450.25x, all divided by x. So that would be our average cost. Okay, the next question is asking us to find what is the average cost when we have 620 clocks. Okay, so my average cost is my C of x bar, and 620 would be my x. So we'll plug those things in. So we have C of x bar, we don't know that, but we do know that x is 620. And we're going to divide the whole equation by 620. So you're going to need a calculator on this test, so make sure you have one that you like to use and you're comfortable with using. I'm going to plug that in and just kind of figure out what that is. All right, so I just plugged it into my calculator, and I also photomathed it to make sure my calculator did it right. I got 491.12. The decimal went on forever, but I'm going to round it to the hundredths place because money is usually rounded into the nearest penny. So there we go. Our average cost when we produce 620 clocks is $491.12. Okay, let's look at this next one. This last one is asking us, it's saying how many clocks, so that's what we're trying to find, should be produced to have an average cost of $592.50. So I'm going to know that I need to find my x when I have my average cost. So I'll plug 592.50 in for my average cost, and then solve for x. Okay, there we go. So we need to solve this equation for x. So I'm going to multiply both sides by x to get my x out of that denominator. We have 592.50x equals 25340 plus 450.25x. Okay, then I'm going to subtract the 450.25x over. So that's 450.25x. And we get here, if I have 50 cents and I take away a quarter, I have 25. And then I have 142.25 equals 25340. All right, so I'm going to go 25,340 divided by 142.25. Okay, and when I do that, so let's see, 142.25 on both sides. I end up with x is 178.14. Okay, let's talk about the context of this, because I'm trying to figure out how many clocks should be produced. So this means when I want an average cost of $592.50, I need to produce 178.14 clocks. But can you produce 0.14 of a clock? The answer is no, you can't. So we're going to just round that to 178 clocks. We'll just round to the nearest whole. Okay, so 178 clocks gives us about an average cost of $592.58. So we needed to round it because we can't have 14/10 of a clock. We can only have whole clocks that are made. So there we go. That is question 6 and the end of page 3. Okay, that was also the end of our fraction stuff. I think we might have one or two more things kind of pop up, but we're going to look at now simplifying these radical expressions. In the test, it's going to say assume all variables are positive real numbers. That's helpful to us. It helps us know that we don't need absolute values. Okay. So on this one, we have to do order of operations, which says we are going to go 9 plus 16 first, which is 25. And then the square root of 25 is 5. That is different than B, because on B we need to do the square roots before the adding. So we have the square root of 9 is 3. The square root of 16 is 4. That gives us 7. All right, on C, C's kind of interesting. I think there might have been a typo when this test review was written. Because I have the square root of 15 and the square root of 5, I can't add those together. I could maybe say, let's say 15 is 3 times 5, But neither one of those are perfect squares, so there's no simplification there. So because of that, this is actually in simplest form. So there's not anything you can do. D, on the other hand, will have something we can do. Let's look at D here. We can reduce these radicals. So I could rewrite 50 as 2 times 25. And 25 has a perfect square. So I would go 4 times 5 square roots of 2, because I can pull that 25 out of the radical by taking the square root of it. And then my other one is 4 square roots of 32. I can write 32 as 16 times 2. 16 is also a perfect square. So let's bring that out. We can say that is 4 times 4 square roots of 2. So we have 20 square roots of 2 plus 16 square roots of 2 is 36 square roots of 2. And we're done. Okay, question E is going to be a multiple choice type of question. Don't know if I'm allowed to tell you that or not, but this will be a pretty simple one if you know the right things to do. So I have the 16 ninths all to the 5/2 power. The easiest way to go about solving this problem is to start with the square root, or the 2 in the denominator. So I'm going to square root 16 over 9. And then I will take the 5th power after I square root. So the square root of 16 is 4. Square root of 9 is 3. Then I want to take 4/3 to the 5th power. 4 to the 5th power is 1024. The numbers that you use will be smaller, so they are ones you can calculate pretty quickly. And 3 to the 5th power is 243. So that is our fraction, 16 ninths to the 5/2 power. Okay, our next one is negative 64 to the 2/3 power. So this will follow the same lines that we just saw. We're going to take the cube root of negative 64, and then we are going to square it. So here we get the cube root of negative 64 is negative 4, and negative 4 squared equals 16. Okay, so question G, this is where it starts getting kind of difficult. We need to figure out what inside this radical can be taken to the 5th power. So let's start with 224. My guess is 224 is going to be 32, or divisible by 32. So if I take 224 and I divide it by 32, I get 7. So I'm going to break 224 up as 7 times 32. Then I have x to the 6th. 5 does not divide in evenly to 6. So I'm going to start working my way down. 5 does go into 5 though. So if I have x to the 5th, I need one more x to make that x to the 6th. Then I have y to the 13th. 5 does not divide in evenly to 13, but it does divide into 10, leaving me with 3 y's left over. And then we have here z to the 15th. Okay, and then I just need to start pulling out my perfect 5th power. So there's a 5th, there's a 5th, there's a 5th, and there's a 5th. So if we pull those out, we're going to take the 5th root of them. The 5th root of 32 is 2. The fifth root of x to the fifth, in that case we just divide the powers. That's just going to be x. The fifth root of y to the 10th is y squared. And the fifth root of z to the 15th is z to the third. Okay, and then whatever is left over just stays inside my radical. And then that is simplified as far as we can go. Okay, last one on this page is h. Let's take a look. So the first thing that we want to do is we want to reduce this fraction. So we want to say, how many times does 5 go into 405? That would be 81. Then I have a to the 9th over a squared is a to the 7th. B to the 20th over b cubed is b to the 17th. And c to the 8th over c to the 7th is c. So we want to simplify that. 81 is a perfect fourth power. So that's really nice. We don't have to break it up like we did on the previous problem. But here I have a to the 7th. So I need to write a to the 4th times a cubed. B to the 17th should be b to the 16 times b. Not 6, but b. And then we have the c all by itself. So here are our perfect fourth powers that can be brought out. We have the fourth root of 81 is 3. The fourth root of a to the 4th is a. The fourth root of b to the 16th is b to the 4th power. Those are what can be pulled out. We will still have an a cubed, a b, and a c inside. And we are simplified. All right, last page here. Question 8. We'll have a question. The top question will be on the multiple choice, and the bottom one will be on the written. So be aware of that. When we need to rationalize the denominator, the very first thing I would do is if I do have any constants, that I write them with a base, the lowest base I can. So for example, 27. I can rewrite 27 as 3 to the 3rd. And what that allows me to do is just take the number down super small so I don't have to reduce really obnoxiously in the end. Okay, we need to multiply the numerator and the denominator by a fourth root so that everything in my denominator can cancel. So for example, I have 3 cubed. How many more 3's do we need to make that 3 to the 4th? We only need one more. We want it 3 to the 4th because 3 to the 4th cancels out with the fourth root. Then I have here x. I have x to the 1st, so I actually need 3 more x's. And y to the 3rd tells me I need 1 more y. Okay, now once we've done that, we can maybe write smaller next time. Just kidding. We have 3xy squared, fourth root of 3x cubed y, all over the fourth root of 3 to the 4th, x to the 4th, y to the 4th. Okay. From here, I'm going to do my fourth root, x cubed y, and in my denominator, I'm going to reduce that fourth root. I have the fourth root of 3 to the 4th is 3. The fourth root of x to the 4th is x, and the fourth root of y to the 4th is y. Okay, we're pretty much done. There is one last thing we need to do, and that is we can reduce some of this stuff. So because they're all outside, we can reduce. We have 3, the 3's cancel, the x's cancel, and one of the y's cancel. So we have y, and then we've got the 4th root of 3x cubed y. So that is our denominator rationalized, which means getting the square root out of our denominator. Okay, the next one, b here, we want to also rationalize this denominator. Okay, we need to make sure we have no square roots in our denominator. So I'm going to multiply the top and bottom by the conjugate of my denominator. Well, the conjugate, and be very careful with this, is 9 plus the square root of 21. Okay, so then I just do my multiplication and my distributing. So I have 4 times 9 is 36. 4 times 21, square root of 21 is 4 square roots of 21. On the bottom here I have 9 times 9 is 81. And the square root of 21 times the square root of 21 is 21. Negative 21. So we've got 36 plus 4 square root of 21 divided by 60. Okay, we can reduce. This is going to be the hardest. So actually this would have been easier to not distribute that 4 through. So I'm going to take my 4 back out. And I'm going to keep it like that. And I'm going to reduce the 4 with the 60 here. And that gives me 9 plus the square root of 21, all divided by whatever 60 divided by 4 is, which is 15. And there we go. All right, let's look at question A on number 9, question A. On this one, we want to isolate the square root first. So we're going to isolate that square root. I'm going to also make it look better. We need to isolate the square root. We're going to subtract the 4 over. So we have the square root of 2x minus 5 equals x minus 4. Okay. Then from here, we want to get rid of the square root. So to do that, we need to just square both sides. That eliminates the square root. But I need to FOIL that right side. If you're good at doing perfect square foiling, go for it. If not, make sure you FOIL it all the way out. But the foiling of x minus 4 times x minus 4 is x squared minus 8x plus 16. Okay, then I need to just bring everything over to the left side. Add the 5, add the 5. So I end up with x squared minus 10x plus 21 equals 0. And that's a quadratic, so we're going to factor to solve. And set each factor equal to 0. Like that. And we have our 2 possible solutions. Okay. There is one last thing we need to do here. We need to check our answers. So I'm going to plug 7 in when x equals 7. So we've got the square root of 2 times 7 is 14 minus 5 plus 4. We want to know, does that equal 7? Well, 14 minus 5 is 9. The square root of 9 is 3. 3 plus 4 is 7, so that checks out. Let's try 3. Square root of 2 times 3 is 6. 6 minus 5 plus 4, does that equal 3? Does 1 plus 4 equal 3? Bummer, it does not. So that means that 3 is not one of our solutions. Our only solution is x equals 7. Okay, so that is our rational equation. I'm not actually going to solve B for you because it is a bonus question if it is on the test, and I want you to be able to do that on your own. But I am giving you a way to practice it without my help. I will give you the answer without doing the work though. On B, our final answer is x equals 8. That's the only answer. That means if there were 2 answers, one of them didn't work, so make sure you're checking your answer. Okay, so that is 9, solving the rational. That says rational. That is a typo, actually. It should say radical. Solve the radical equation. Do make sure you check your answer. Okay, let's look at 10 here. Ooh, 10's a good one. So the thing we're going to do with 10 is we just need to simplify the complex expressions by multiplying them. All right, so this one, we're going to just FOIL. So we have 3 times 2 is 6. 3 times 6i is 18i. Negative 4i times 2 is negative 8i. And negative 4i times positive 6i is negative 24i squared. Okay, a couple things here. We can go 6. We can go 18i minus 8 is 10i. And then we can rewrite negative 24i squared as plus 24. 6 plus 24, 30 plus 10i. Okay, the trick there is knowing that I squared is negative 1. And what that does is it just changes the sign on with what it's on. Okay. With B, we don't want that denominator to have an imaginary number. We need that to go away. And we want to rewrite this as a complex number, not as a fraction. So we're going to multiply the top and bottom by the conjugate of the denominator. Okay, so we're going to distribute here. That gives us 21 plus 15i. And in the denominator, it's 35 plus, no, sorry, that is not 35. Let me fix that. It is 49 plus 35i minus 35i minus 25i squared. Okay, the 35i's do cancel. We have 49 plus 25, which is 74. I lost a 1 there. Sorry. That's a 15i. That's 74. And we need to rewrite this as a complex number. So I'm going to go 21 over 74 plus 15i over 74. And 74 does not go into 15 or 21, or vice versa, or have any common factors. So there we go. Okay, this last one, the C, 2 plus I over 5 plus I. So we're going to multiply the top and bottom by the conjugate. Okay, let's distribute. That's 10 minus 2I plus 5I minus I squared all over 25 minus 5I plus 5I, those cancel out, minus I squared. So that gives us 10 plus 3I plus 1 all over 25 plus 1. So that's 11 plus 3I over 26, which written as a complex number is 1126 plus 3I over 26. There we go. All right, so those are the problems for the test. I think that if you study this review and do some practice problems that are kind of similar to these problems, you are going to be very well off on the test if you feel like you can do everything. Okay, good luck, and come to me if you have any other questions.